Swayam Prabha. Digital India. Educated India.
Good morning. In the last lecture, we looked at the application of the force method to analyze a statically indeterminate truss. It was a simple truss with a single degree of indeterminacy, and as we go along, we'll run into more and more complicated problems. So therefore, I'm always going to start with a simple problem. So last time we looked at a simple problem at how to use the force method, and the basic concept of the force method is what I established. Let us write that down again. What was the basic idea behind the force method? The basic idea behind the force method can be written down in the following method. One, determine static indeterminacy. 2, identify redundant forces. Now, how many redundant forces? Well, whatever is your static indeterminacy, you need to identify that many redundant forces. What do you mean by redundant forces? In other words, we are going to define a base statically determinate structure in which the forces corresponding to the redundance equal to 0. So that is the reason why we identify the redundant forces, so that we can define a base statically determinate structure in which all the forces corresponding to the redundance is equal to 0. What's the next step? Next step is find the displacements corresponding to redundant forces in base structure. Okay, so what you do is you define the base statically determinate structure, find the displacements corresponding to the redundant forces in the base structure, find the displacements due to redundant forces only, and 6, apply compatibility condition. This 6 steps totally define the force method, and that is what we have done in the previous lecture. If you remember, let me just quickly review the previous lecture. We had, this was our base structure. We identified the static indeterminacy, and we identified the redundant force was the force in member BD, which we called as X1. So therefore, this was the base structure where we had the loads, and the force on BD was equal to 0. Then we added the structure where the force due to X1 was force X1 was given, and we found out the forces. And essentially, if you look at it, find the displacements corresponding to redundant forces in base structure. We found out the displacement here due to these forces. Find the displacements due to redundant forces only. We found out the displacements in this structure due to the redundant force, and then we applied the compatibility condition. What was the compatibility condition? The compatibility condition was that the actual delta, which is equal to the due to the loads alone, due to the redundant, actual delta was equal to 0, and from that we solved and we got the redundant forces. Okay, that is the force method. Okay, so now this lecture I am going to be applying the force method to a beam. And understand one thing, and that is that you have to be able to find out the displacements, and to find out the displacements in this structural analysis that I am going to be doing. Remember, I said to find displacements I'll always use the virtual force method. So therefore, the whole process over here is based on the virtual work principle. Remember, I said that I was consistently going to use only virtual work, and that's why here in this, where do we use virtual work? We use virtual work to find out the displacements. So that is the overall concept that I'm going to be using over and over again. Now let's look at a statically indeterminate beam. And let me put a loading here. Let's say that these are 10 meters, okay, and this load is 10 kilonewtons. So this is a 2-span beam. Each span is 10 meters, and the load applied at the center of the span, so this is 5 meters, so this is A, B, C. Think of it as a 2-span bridge, okay, supported on 2 abutments and a central pier. Okay. And we have a static load of 10 kilonewtons applied at the center of span AB. And we have to find out the bending moment diagram for this structure. Okay. So that is what we have to do in this particular case. We have to find out the bending moment diagram for this. What is the static indeterminacy of this? We've done this over and over again. The static indeterminacy, if you look at it, there are 4 reactions, 3 equations, so static indeterminacy is 1. What is the base structure? I'll make this the base structure. I'll say I'll identify this force as my redundant. Since it's only single indeterminacy, I need to identify one, and I'll take this one. You could have taken any one of them, it's up to you. Okay, only thing is you cannot take a redundant that will make the structure unstable. That's all. You have to maintain the structural stability, and as long as your structural stability is maintained, it doesn't matter how you define it. And so therefore you could have taken this, you could have taken this, you could have taken this. Any one of the verticals reactions could have been taken as redundant. You can do that, and it's not a problem. However, in this particular case, I opt to take the reaction at C as my redundant. So therefore, what is my base structure? My base structure becomes this, because this x1 is equal to 0. Remember that in the base structure, this reaction, which is x1, is equal to 0. And of course, in this I have the load. Now, what is this equal to? This is equal to this plus do you agree that this plus this is equal to this? Obvious. So therefore, what are the steps here? Understand that this is the redundant. So what do I have to do? In this case, I have to find out the displacement x1 due to the loading. Then I need to find out x1 due to the redundant. And what is the actual x1 in this particular? So the displacement of this point, since it's vertically restrained, is going to be equal to 0. And therefore, if you look back at this, so therefore all we are saying, our compatibility condition is x1L plus x1x is equal to 0. This is our compatibility condition. Okay. So therefore, the whole point over here is to find out these two displacements, and once we find out those two displacements, then we add them equal to 0 and we get our equation, that single equation that will then be able, we can then solve for x1. Okay. So let's go back. So we're going to now start solving the problem. Okay. So let us now solve this problem that we are going to be able to get it. Okay. Let's look at the base structure. And the objective of this problem is to find out the displacement, the vertical displacement of this point. That is the whole idea behind this. Well, this is a statically determinate structure and you have to find out the displacement. Simple. I am going to be using the principle of virtual force. Since I am finding out displacement, I have to use the principle of virtual force. So this, what is the step that I go through? Note that basic assumption over here is what? Is that only flexural deformations. In other words, only flexure is considered, shear deformations are neglected. Okay. Now you know how to compute flexural deformations, right? Using the virtual work principle. Well, let's go through a little bit step by step. You will see that when I have a member which is subjected to a moment M, what happens actually under this effect? Under this effect, this structure actually, plane sections remaining plane, it goes something like this, where at the neutral axis it remains the same dimension as it was here. This compresses, the top part compresses and the bottom part expands. And this is, and the plane section, this section remains plane. Original is this. After deformation it becomes something like this. So plane sections remaining plane, the simple beam hypothesis. And if you look at this, we can say that, well, what we are interested in essentially is the movement of this plane relative to this plane. So we can actually draw it in this fashion, that this plane has not moved, only this plane has moved. It's all relative, right? So deformation is all relative. So this is what we are interested in. So if you look at this, okay, what is the curvature? By definition, curvature is the rate of change of theta per unit length. That is curvature. Curvature in a lot of places is given as kappa. Okay, I don't care how you define it, this is curvature. And this in simple beam theory is given by m upon EI. Curvature is given as m upon EI. Okay, so that is your curvature. So therefore, if my curvature is this, what is this? This is length dx. What is these d theta? D theta is given by m upon EI dx. So given an m and given EI value, okay, the d theta is equal to m upon EI dx. Okay, so that is the real deformation due to a applied moment m. Okay, and if you want to find out the work done, virtual work done by this deformation when undergoing a virtual moment small m, then the work done, if you look at it, the total virtual work done, internal virtual work done, is going to be equal to, over this infinitesimal area is going to be small m into d theta. Small m into d theta. That is for the infinitesimal length dx. So that integrated over the entire length is going to be my work done. And note, if you look at it, since m is in this direction, theta is in this direction, they are positive, and d theta is given this way. So this becomes 0 by L m upon EI dx. So the internal virtual work done due to flexure is given by the moment at a particular point multiplied by the real curvature integrated over the whole length. Okay. So if we do that, what do we have to do then? We have to, if we are using the virtual force principle, we find out the bending moment due to the actual load. We find out the bending moment due to the virtual force applied corresponding to the displacement that you are interested in finding out, and then you are going to integrate it over the whole length, and that will give you the work done, and that you can equate to whatever external work that you need to do. Okay. So this is due to flexural deformations only, and in a beam we only consider flexural deformations. It's fundamental. Okay. So therefore, what we need to do here is find out the displacement in this particular case. To find out this displacement, what we do is find out the bending moment due to this force. Then we find out the bending moment due to, see, we are trying to find out this displacement, and because we are trying to find out this displacement, therefore you have to then look at it from the point of view of, you have to apply a virtual force corresponding to this displacement, and then once you find out the force due to this displacement, okay, you need to then take out, apply a virtual force, find out the bending moment due to that, and then you need to go through the virtual force method. So let us do this process. Find out the bending moment due to the applied load. The applied load is 10 kilonewtons. So now how do we find out the bending moment? Well, again, I am not in this particular course going to actually go through all the steps of finding out bending moment, shear force, axial force diagrams. Never. I'm going to assume that you know all of this, and if you find it difficult understanding how I am doing all these, finding out the bending moments and shear force diagrams, I recommend that you go back to your first course in structural analysis and review how to get bending moment diagrams. In this particular thing, during this lecture, I'm going to be assuming, just going through the steps as if you know how to find out the bending moment diagram, and I'm not going to go through the steps of finding out the bending moment diagram. Okay, so here 10, this is going to be 5, 5, and the bending moment diagram is going to look like this. Note that this is 10 meters, so this is going to be equal to 25 kilonewton meter, and the sense of curvature is going to be in this way. I always draw, I never, it's my point never to say positive moment, negative moment. I always draw the bending moment diagram and then show the sense of the curvature so that you know what kind of moments are being applied at that particular point. Okay. So here this is the bending moment diagram for your real load. What's the next one? We need to find out the bending moment diagram for a virtual load, because we need to find out the displacement at this point. So when you find this out, you will see that this is equal to 1 and this is equal to 2, and the bending moment diagram is going to look like this. So this is my M diagram. This is my small m diagrams. Okay. And now what I need to do is, I need to be able to, the work done will be, the internal work done is going to be equal to integral over AB small m dx plus integral over small m capital M upon EI dx. We will assume that the EI for both spans are equal to, are the same. Okay, but look at this. If you look at BC, in BC, what is M? M is equal to 0. So therefore, if you look at this, this essentially becomes integral, since this M is equal to 0, this becomes only over AB, this integral. Now, you already know how to do these integrals when you have straight lines. You've already done this in your solid mechanics course, right? see, for example, therefore, in this particular case, we have this so this is going to be 25. This is over AB, since we are only integrating over AB. This is my capital M diagram. Okay, this is at 5 meters, and then I have my this is my small m diagram, and essentially one way of doing this is finding out the expression from A to midpoint, then another expression for M from midpoint to B, and then taking this also as a function of x, integrating from 0 to 10, and you can actually get it. You can actually get it analytically. I am going to use the simpler method, which says that the area under this curve, and look at this is essentially an area under the curve. When you are doing integration of any function over dx, what are you doing? You are actually finding out the area under this fx curve. Okay, so this one, if you look at it, is going to be equal to, now this I am going to divide by EI, so I will call it the M upon EI diagram. If you look at this is the M upon EI diagram, this is the small m diagram, and what you are doing is over M upon EI, which is this one, into this multiplied by this into dx, is equal to the area under any one of these curves. The area under any one of these curves. Note, of course, that this has to be separated from 0 to 5 because the expression for m is different. So it's going to be this plus 5 to 10 mm upon EI dx. So this part and this part have to be done separately. Okay, and this integral I'm going to use is given by area under any one of these curves multiplied by the, so we can say, let's say for example, the area under the m upon EI curve multiplied by the m bar value, the m value at the CG of this area. This is how integration is done, and if we use that, you will see that the m upon EI is equal to, is given in this particular case. See, this is 0 upon 25, so the area is 5 into 25 upon EI into half. Half length into base. So that is for this one, and multiplied by, where is the CG? CG is 2/3 of the distance from here, so that is at 10 by 3. So at 10 by 3, since this is 10, at 10 by 3, what is the value? The value is over here, the value is going to be 10 upon 3. So that is for this one. Now next, let's take this area. So this area is also, and note that both of the same sense, that's why it's positive. Okay. Similarly, if you take this one, that's also going to be 5 into 25 upon EI into half, multiplied by, where is the CG? The CG is at this point, and that is 10 by 3 from here. So if you look at this, the value will be 20 by 3. So if you add all of them up, you will see that this is equal to, okay, 10 by 3, 10, 5. So you're going to get 625 upon EI. That is the work done by the internal deformations. the internal flexural deformations. And what is the work done by the external? External is nothing but 1, this is internal, and the external is equal to 1 into x1L. So that implies that x1L is equal to 625 upon EI. What does that mean? Let's look back at what this means. This means that due to this load, this displacement is equal to 625 upon EI. So if you look back at this problem, the original, we have found this out. The next step, to find this out. How do we find that out? Well, let's go. Simple, right? How do we find that out? Well, we find out due to this load, we find out the bending moment diagram, then we apply a unit load here and find out the virtual bending moment diagram, and that's how we do it. Okay, note that all of it involves this load itself, for which we have already found out. If you look at it, we've already found out the bending moment diagram. So I'm going to now utilize that. I'm going to apply x1 equal to 1, find out the work done, and then the total displacement is going to be multiplied by x1, the unknown, right? Okay, for this we already got our bending moment diagram. We've already drawn it. What is it? It's like this, right? And this is equal to 10. So therefore, again, this is the real capital M diagram. The capital N diagram will have 10 into x1 upon EI. That is the bending moment M upon EI diagram for a load, for the actual load x1. Now for the unit load x1, which is my small m diagram, this is going to be equal to 10. This is my small m diagram, because I am trying to find out the displacement at the same point. Okay, so now once I have that, I'm just going to go ahead and calculate the internal virtual work. The internal virtual work is nothing but, this is 10 meters, this is 10 meters. So the internal virtual work is 10 x1 upon EI into 10 into half multiplied by the value at this cross section, which is equal to 20 by 3. Okay, and that is again same thing we do on this side. You will see that you'll get the same exact thing, 10 x1 upon EI into 10, that is the area, and this is the moment at CG. So what you get here is you're going to get 2000 by 3 EI x1. That's the internal virtual work. What's the external virtual work? We've already got it, 1 into x1x. So this implies that x1x is equal to 2000 upon 3 EI x1. So therefore, we have computed this, and therefore now we apply the compatibility condition. The compatibility condition is going to give us what? x1L we've got is equal to 625 upon EI, x1x is equal to 2000 upon 3 EI into x1. Compatibility condition, x1L plus x1x equal to 0. This implies that 625 EI plus 2000 upon 3 EI x1 is equal to 0. This implies that x1 is equal to minus 1875 upon 2000, which is equal to 1875 upon 2000, which is equal to minus 0.9375 kilonewtons. Once I have this, note something very interesting. How do I get the bending moment diagram for the entire thing? Note that once I have got x1, now I have this structure. I now know x1. This is equal to minus 0.9375 kilonewtons. So I have this load. Okay. Now can I find out my reactions? Of course I can find out. I can find out everything. I can draw the bending moment diagram. Actually, if you look at it, let me draw this. You can get this, that is going to be due to this load, it's going to be 5 here, and due to this it's going to be, in other words, when this is minus, it essentially means that the load is in this direction plus. So the load at this point is acting downwards. Well, that makes sense, because when you do this, this tries to pull it out, and this load keeps, acts downwards to pull it back there. That's what this means. Okay. So therefore, if we look at this, this is going to be equal to 1.875. So this is going to be 6.875 kilonewtons. This is going to be 4.0625 kilonewtons. This is going to be the total loading that you have, reactions, and once you have the reactions, you can of course draw the bending moment diagram. You will see that in this particular case, this will become, the bending moment diagram will look like this, with this equal to 9.375 kilonewton meter at this point, and here we get the value over here is going to be equal to this into 5. So if you look at that, that's going to be equal to 20.3125 kilonewton meter, and this is going to be in this way. So this is going to be sagging, and this part is going to be hogging. We've got the bending moment diagram using the force method. Okay, so in a sense, you have looked at, I know that you probably have studied force method to begin with. However, I have spent 2 lectures looking at the basic concepts of force method, just to kind of review if you have studied, and if you have not studied, then there is sufficient detail in the last 2 lectures that I have talked about to be able to give you an overview of how to use the force method to analyze a structure. So when you have flexural deformations, the basic concept remains this, that if you have the statically indeterminate structure, define redundant forces. Once you have redundant forces, the base structure has redundant forces equal to 0. Find out the displacement corresponding to the redundant force in the base structure, apply the redundant force and find out the displacement of that particular point, and then superpose the 2 displacements, because after all the 2 structures together form the actual original structure. Superpose the 2 displacements and find out what the displacement in the real structure is, and apply the compatibility condition to find out the value of the redundant force. and once you found out the value of the redundant force, then you've got essentially a statically determinate structure for which you can find out the axial force in the members in a truss or the bending moment diagram and shear force diagram for a beam structure. Okay. So now I would like to spend a little bit of time saying how do we take this forward for a frame. So I'll just spend 10 minutes talking to you about how to use this for a frame. So let us take a simple frame. I'm not going to solve this problem today because during next few weeks we are going to solve enough number of problems. I want to just introduce to you the concept. Let's say that I have gravity loading and some wind loading maybe on this structure. Okay. So now how do I find out, by the way, what is the redundancy of this structure? If you look at it, you will get static indeterminacy 1. Okay. Static indeterminacy 1. Which one would I take in this particular case? You can take any one of them. Okay, it doesn't matter. But I will take this as my redundant, in which case automatically my base structure becomes this, because this is equal to 0 in the base structure. So my base structure, so let me say F1, F2, so I have F2, F1 plus so this is equal to this plus this, and so therefore how do we solve the problem? Well, actually again in this case, due to these loads we find out what is the displacement corresponding to the redundant. Since this is free to move, it will move. Then we find out due to this how much this moves by. So that is x1x. And in the real structure, how much does this point move by? Nothing. So x1L plus x1x is equal to 0. Now, the point here I would like to make is that how do I find out this x1L and x1x? Okay. In a frame. We've already done that for a beam. In a frame, how do we do it? Understand one thing, that the only difference between a beam and a frame is that it's got different way of computing bending moment diagram. That's all. Otherwise, even in the frame, we only consider flexural deformations only. Why? Well, we neglect axial deformations, they are very small, and we also neglect shear deformations because they are small. Somewhere after a few lectures, I am going to actually look at the relative value of the axial deformations and shear deformations in normal situations and show to you that in normal situations you can neglect axial and shear deformations. But in some specific kinds of situations, you may not be able to not consider axial and shear deformations. So in those cases, you might have to consider all three. But then, this is the beauty of the virtual work method, because all you need to do is find out the work done due to the flexural deformations, find out the work done due to the shear deformations, find out the work done due to axial deformations. Remember, work is a scalar. You can add up all the work done by all the deformations and get the total work done. Okay. So now let us look at the flexural deformations in the frame. I'm just going to go one step. So what is this? Let's look at what it is that we are interested in. We are interested in finding out this displacement due to these loads and this displacement due to this load. Let's see what happens. All I need to do really is, this is a statically determinate frame. You should be able to find out the bending moment diagram for this. How would you find out the bending moment? Well, find out these reactions. This reaction sigma fx is going to be equal to F1, okay, and these due to this load is going to be F2 by 2, F2 by 2, and due to F1, let's say that this is 5 meters and so is this, so then this will become plus F1 and this will become minus F1. These are the reactions. This is this, and so bending moment diagram, how will it look? If you look at this, this is going to look in this fashion. I'm going to draw it any which way I want because I'm always going to show the sense. The sense is going to be, in this particular case, in this fashion. And what is the value over here? This is going to be equal to 5F1. What is the value over here? By the way, continuity, so you have to have 5F1. What's going to happen over here? Well, depends on the relative values. What is the bending moment in this section? Note that there is no shear, so if there is no shear, it's here. So therefore, this particular case, it will probably go something like this, and here it's going to be in this fashion. Here it's going to be in this fashion. The particular values will depend, but you've got it. You've got your M diagram for the frame, for the given loading. Now, what is your small m? Small m is going to be put unit load here. Put unit load here and find out the bending moment diagram. Note that in this particular case, this is going to be 0, this is going to be 0, this is going to be equal to 1. And if you look at the bending moment diagram for small m diagram, this is going to be 5, 5, 5 with this in this fashion. This is going to be this fashion. This is going to be this fashion. That's your small m diagram, and then you follow the same procedure to compute mm upon EI dx for each member, add them up, and you have your total work done, and so you can compute, and external work is going to be 1 into x1L. From that you can find out your x1L. You see, the basic point is that there is no difference between a beam and a frame as long as you consider only flexural deformations. The only thing that happens is that in a beam everything is in one plane, along one line. Okay, in a frame it's spaced across the plane, so you have different. So the only thing is that the equilibrium conditions look different. Otherwise, once you have the bending moment diagrams, whether it's a beam or whether it's a frame, it does not really matter. Okay, so therefore beams and frames are really going to be the same problem, and I'm not going to treat them in any different way. It's only that the equilibrium conditions give rise to different sets of equations. That's all in a frame as opposed to a beam. There's nothing else. For example, in a beam you may not have horizontal forces at a hinge, because you normally only have vertical forces on a beam. Okay, whereas in a frame you have both gravity loads as well as horizontal environmental loads due to wind or earthquake, and therefore you would have horizontal forces, reactions at hinges, which really, if you look at it, does not matter one way or the other. After all, if you know how to compute the bending moment diagram for a beam or a frame, that's all that is required for you to be able to successfully apply the force method. Okay, and we shall continue solving problems, etc. But I want to now introduce the fact that if you look at it, you see this. I have a situation where I have a reaction and the displacement corresponding to the reaction is always 0 because it's fully restrained. Okay. Now, next lecture onwards, I'm going to look at a situation where you have a partial restraint. In other words, you can develop a reaction, but the displacement in the structure need not necessarily be equal to 0. How would you treat those kind of problems? Those are essentially flexible support conditions that you are aware of. So next time we're going to look at something new, flexible support. We're going to look at other kinds of situations. What happens if a member is not exactly the size that in its geometry it's supposed to be? That's called a lack of fit. Then you may have temperature stresses, erection stresses. How do you analyze the structure for all those kinds of situations? We shall see how we can apply the force method for all those kinds of situations over the next few lectures. Thank you very much and look forward to seeing you the next lecture. Bye.